Hi, the application of an stochastic or learning solver must carefully consider several important aspects as we will see in the following few minutes. In this lecture, we study key considerations concerning with the selection and testing of stochastic or learning solvers. Generally speaking, a stochastic or learning optimization solver follows an iterative and adaptive search procedure to explore complex solution spaces. It begins with initialization, where one or more candidate solutions are randomly generated within the variable bounds. These solutions are then assessed through fitness evaluation, where objective function and possibly constraint handling determines their quality. Next, a termination criterion check is performed, for instance, maximum iterations or convergence. If not satisfied, the solver proceeds to generate new solutions by applying stochastic variation or learning-based updates, like mutation, recombination, or policy-guided moves, often balancing exploration and exploitation. This cycle repeats with the solver progressively refining solutions based on accumulated information until a stopping condition is met and a high quality of their near optimal solution is obtained. Choosing a stochastic or learning solver for optimal power flow requires balancing several evaluation criteria, as no single method is best in all contexts. Example solvers are basic and modified versions of genetic algorithms, particle sort optimization, and differential evolution. Solution quality reflects how close the result is to the true optimum and how well constraints are satisfied, which is critical for both operational reliability and cost efficiency. Robustness measures consistency across runs and scenarios, which is essential in optimal power flow due to uncertainty, for instance, due to variability of demand or renewals or the failure of components. Convergence speed determines how quickly a good solution is found, especially important in short term, like real-time or near real-time operation. Computing before, that means time and resources, becomes a limiting factor in large scale or multi-scenario problems. These criteria inherently involve trade-offs. Faster methods might reduce numerical accuracy, while higher robust or high-quality solutions might require more computation. In short-term optimal power flow problems, speed and reliability dominate. In mid-term asset management problems, a balance between quality and computational cost is needed. And in long-term system development problems, robustness and solution quality are prioritized even at the expense of higher computation effort. In short, solver selection depends on aligning performance criteria with the time horizon and decision requirements of the power system problem. Random number generators, typically pseudorandom, play a central role in the performance of any stochastic or learning solver, as they drive key processes such as initialization, exploration, and variation. In popular tools like MATLAB, the rand command is commonly used to generate pseudo-random numbers. The effectiveness of the rand command depends on proper use of the random seed, for instance generated via the RNG function, which controls reproducibility. Fixing the seed enables consistent comparison during algorithm testing, while varying it supports robust Monte Carlo evaluation by exposing variability across runs. The rand command illustrates the dual role of randomness. That means it drives exploration during the optimization, but must be carefully managed and systematically tested to ensure reliable and unbiased performance assessment. The quality of randomness, that means uniformity, independence, reproducibility via seeds, directly affects the diversity of solutions, convergence behavior, and robustness. Poor or biased random sequences can lead to premature convergence, reduced exploration, or misleading performance, while good generators enable consistent and reliable search dynamics. In contrast, algorithm performance testing aims to objectively assess this stochastic behavior, often using a Monte Carlo procedure. This involves, first, running the optimization algorithm multiple times with different random seeds. Second, storing performance metrics from each run, like objective function value, convergence speed. Third, applying a stopping rule for the number of runs, like fixed repetitions or statistical confidence. And fourth, analyzing results statistically, like computing means, variance, best, worst cases, to compare or improve algorithms. In short, randomness drives the search while Monte Carlo evaluation controls and quantifies its effects, ensuring that observed performance is reliable and not due to chance. When evaluating stochastic or learning solvers via Monte Carlo runs, generic statistical measures provides a concise and reliable way to compare performance. Metrics such as mean and median reflect central tendency, like overall solution quality, while standard deviation or variance indicates robustness and consistency across runs. Additional indicators like best, worst values, and percentiles help capturing extremes and distribution spread. Box plots are especially insightful as they visually summarize the distribution of results, the median, interquartile range, and potential outliers. This allows quick comparison of algorithms in terms of performance level, like central lines, stability, box size, and reliability, presence of outliers. In essence, statistical measures quantify performance, while box plots provide an intuitive visual comparison, ensuring that conclusions are based on consistent behavior rather than isolated outcomes. In Monte Carlo-based evaluation, success rate-oriented metrics assess how often an algorithm meets predefined criteria, such as constraint satisfaction, convergence to a target or near to optimal value, or simply producing feasible solutions. This perspective is particularly relevant for constrained problems like optimal power flow, where feasibility is as important as optimality is. And it provides an intuitive measure of algorithms' performance from a numerical trustworthiness point of view in practice. However, success rate evaluation has limitations. The definition of success can be arbitrary, for instance, tolerance thresholds for optimality or feasibility, which might bias comparisons. It also typically requires a large number of simulations to statistically estimate the meaning of these metrics, increasing computational cost. Moreover, it might overlook nuances in performance quality, since different solutions can be classified as successful, but they can still vary in optimality. In essence, success rates are valuable for capturing practical reliability, but should be complemented with statistical performance metrics to provide a more complete and less biased assessment. The no-free-lunch theorem in optimization states that no algorithm is universally superior across all possible problems. That is, performance gains in one class of problems are offset by losses on others. This has important implications when comparing algorithms. Results obtained on a specific benchmark set, like optimal power flow cases or synthetic functions, are problem-dependent and cannot be generalized. In practice, this means that algorithm comparison should focus on relevance to the target problem class rather than seeking a universally best method. It also justifies the use of diverse benchmarks and performance metrics, as well as hybrid or adaptive approaches that tailor the search strategy to problem characteristics. In essence, the no-free-lunch theorem reminds us that algorithm effectiveness is contextual, and fair comparison requires aligning evaluation with the intended application domain. When comparing stochastic or learning-based algorithms, supplementary statistical tests such as Wilcoxon tests or F-text or the t-text provide rigor beyond descriptive statistics. These tests help determining whether observed differences in performance, like solution quality, conversion speed, or robustness, are statistically significant rather than due to random variation inherent in stochastic methods. For example, the Wilcoxon test is non-parametric and suitable for comparing paired algorithm outcomes without assuming normal distributions, while t-tests and f-tests assess differences in means or variances under specific assumptions. Applying these tests increases confidence in conclusions, reduces the risk of misinterpreting chance effects, and supports objective, reproducible algorithm evaluation. So, statistical tests complement Monte Carlo analysis by validating performance differences, ensuring that algorithm selection is based on meaningful evidence rather than incidental outcomes. This concludes our video, where you have learned about how to select and test solvers to tackle applications of optimal power flow optimization. Thanks for watching.